Hello everyone. In this video, I am going to talk about section 6.4 simple trusses. In this section, basically, we're going to talk about the method of sections. In the last video, we talked about method of join, which we're going to go around the trusses, each join, one join at a time. We're going to do our analysis. In this one today, we are going to learn we can divide the trusses into two parts by taking a imaginary cut over here. And notice that it's imaginary cut. We're not actually cutting it, but we imagine that we're cutting through there. Since truss members are subject to only tensile or compression forces along their length, the internal forces at the cut members also will be either tensile or compression with the same magnitude as the forces at the joint. This result is based on the equilibrium of principle in Newton's third law. We want to decide how you need to cut the truss. This is usually based on what member of the forces you want to determine. And then where the total number of unknown forces should not be more than 3 in general. And decide which side of the cut truss will be easier to work on. So because we're doing this imaginary cut, right? One truss becomes 2. So which part, the left, the right, the up, the down, which side of the truss you're going to use to run your calculation. And usually the goal is to minimize the number of external reaction. And step number three, if requires, determine any necessary support reaction by drawing the free body diagram of the entire truss and then write our equation. So number 4, draw a free body diagram of the selected part. After you do your imaginary cut, you do the free body diagram of that cut part, right? The part of the truss, and you need to indicate the unknown forces at the cut member. So initially, you may assume all of the force members in tension as done when using the method of join. When you're solving them, if the answer is positive, then the member is tension. It's the same as what you originally assumed. If the answer is negative, then the member is in compression. Please note that you can assume forces to be we can assume either tension or compression, just like the problem that we see, the group problem in our last video. We can assume tension or compression. Just be careful, keep in mind, make a note of what you assumed, and check if it's positive or negative toward the end to see if your assumption is correct. And then number 5, apply the scalar equation, sigma fx equal to 0, sigma fy equal to 0. You probably need another one, moment equation. Okay, so please note that in most cases, it is possible to write one equation to solve for one unknown directly. So look for it. Look for the simplest equation to solve for the unknown that has only one unknown. Solve for the equation that has only one unknown first. Let's take a look at an example. So what we're looking for is the forcing member KJ, KD, and CD. So we know that our imaginary cut will be this purple line right here, which pass through KJ, KD, and CD. Okay, because when we do that cut, these forces, internal forces, will become the, I will put an air quote here, external force, because they're internal force, but since we cut them, the internal kind of explodes out, it becomes the external, right? So it will help us figure out what's the force member in KJ, KD, and CD. If this problem we're doing the method of join, it will be slightly more complicated because there are so many joins here. Method of section will be easier. Now, before we do our cut, we want to do the free body diagram for the entire truss. Entire truss at point A is a pin support, at point G is a roller support. Okay, so we can do the entire truss reaction at A. So since point A, let me annotate right here. Point A says I'm a pin support. I could provide AX and AY. AY the vertical, AX the horizontal. I could do that. And then point G is the roller support. I could provide only in the y direction, your GY. And then you have AY and AX. However, When I write for the entire truss, when I write the equation sigma fx equal to 0, the only force along the horizontal direction is my ax equal to 0. So yes, we can do ax, we can do, this means that a is a pin support. I can provide horizontal constraint if needed. However, right now, because all the forces are vertical, it's not needed. Okay, so that's why ax equal to 0. And then we do a summation of moment about point G to find out the value of ay. Okay, so do a sum of moment about this point, about point G. We have three known forces: 20 kilonewton, 30 kilonewton, and 40 kilonewton. And then we know all this moment arm over here. And then the last one is your ay. Ay, the magnitude times the distance to help us figure out the magnitude of ay. Now we're going to take the moment about point D. We do our imaginary cut. That cut pass through KJ, KD, and CD, pass through that cut. And then these three members, remember they were internal forces, now it sort of become the air quote external. We're doing a moment about point D, which is the point that is not sort of drawn here. Let me do this note a little better with the black marker right here. And the reason that we do sum of moment about point D is that at point D, we have the most unknowns. We have the unknown FKD, we have the unknown FCD. Two unknowns pass through point D, which is the axis rotation, meaning both FKD and FCD have zero moment arm. Okay, so meaning if I'm doing a summation of moment about this point, the only unknown I have is the FKJ. And I know the moment arm for FKJ is 3 meters. So this is one equation I can solve for one unknown FKJ. And again, assuming FKJ is to the right, originally assume, oh, it come out to be negative, it means, oh no, it's the opposite of what we originally assumed. That means instead of tension, FKJ is in compression. Now use sigma fx equal to 0, sigma fy equal to 0 for all the forces that we see here, including your FKJ, the horizontal vertical component that we're breaking down for FKD, and then the FCD looks like only have the horizontal component. So we're putting them together, two equations and two unknowns that will help us solve the FKD and FCD for sigma fx equal to 0 and sigma fy equal to 0. Okay, and then next group problem here, we're looking for the forcing member ED, which is this one, member EH, which is this one, and member GH. And it is pretty obvious that we are going to do our cut like this. But before we do our cut, we're going to do the free body diagram or the force analysis for the entire truss. We're going to do a sum of moment about point A. And the reason we do about point A is a pin support. There is going to be AX and AY. You can see, look, external forces got horizontal and vertical. So I don't know AX, I don't know AY, and they're there. We do a sum of moment about point A that has the most unknowns that will help us to figure out the FY, the vertical reaction force at point F. Okay. And then after that, we're going to do our cut. We're going to do our imaginary cut, which will be right here. And then after we do our cut, we're going to use the left side of the truss to do our write our equations because it's smaller. We're going to do sum of moment about point E, which is this point right here. And again, we pick this point because both FEH and FGH pass through that point E. When it pass through that point E, both FEH and FGH has zero moment arm. They will have zero moment arm. I can eliminate both of the unknowns when I'm writing sigma moment about point E. And the only unknown that I have in this equation when I do sigma moment about E is is going to be, let's see, FED. FED. Sorry, this is point H. I keep on saying E. Sorry, my bad. I was pausing for, yeah, for point H. We're gonna, I was on this equation down here. Sorry. Yeah, we're doing a moment about point H. Both FEH and FGH are two unknowns. They have zero moment arm. I can eliminate the unknown, and then the only unknown that we're solving writing this equation is FEB. And then you can do sigma Fy equal to 0 to solve for FEH. Also, we can do sigma moment about point E to solve for the value of FGH. And the reason being, when you do a sum of moment about point E, two unknown pass through that point E, which one of them is ED, one of them is EH. Both of them, if you haven't get to the, if you haven't write the H equation, moment H equation, you do the E equation. We don't know both of them, but doesn't matter. Both of them go through the axis of rotation. And if you want to do sigma ME, moment about point E equal to 0, the only unknown that I have is FGH. Okay, we can calculate the value of FGH. All right, that's what I want to show you in this section. Please let me know if you have any questions, and thank you guys for watching. I will see you guys in the next one.